This is video 3C for the Year 12 Mathematical Methods course. In this video, we're going to cover the theory behind inflections in shape under the topic of applications of differential calculus. Specifically, we are going to explore the geometrical application of the second derivative, how the second derivative links to the concavity and shape of different functions, the definition of an inflection point, the different types of inflection points and how to identify each, the link between stationary points and the second derivative sign diagrams, how to sketch the graph of a function from its first and second derivative function graphs, strategies to solving exam style questions, and then we're going to cover some example questions. In our last chapter, we covered quite extensively some very key applications of the first derivatives of functions. So we looked at how we can use the first derivative to not only find out where the stationary points are of different functions, so that's, as a reminder, the maximum, minimum, and we can also find stationary inflections of particular graphs, but we can also figure out where different graphs are increasing and decreasing. And all these different attributes are very important for us to not only understand the nature of whatever is being graphed, so whether it's be money or area or volume or whatever, but it also allows us to graph out the function very accurately without the need of technology, which can always be a very handy tool to have under your belt. So then the question is, well, we've also considered finding the second derivative for a bunch of different functions. So then what is the application of the second derivative? And that is exactly what we're going to be covering here. So when we're talking about the application for the second derivative, we are going to be considering the shape of graphs, or in other words, the concavity of graphs. Now, let's do a quick bit of revision from stuff that you probably would have had a look at last year. When we're talking about the word concavity, we essentially mean which way does the graph open up to. So for example, if you have a region of the graph which goes upwards like this, then we call this concave up. Whereas if you have a graph that goes down like this, then we call this concave down. And what the second derivative can be used for is to determine when the graph is like this and when the graph is like this. Now, if we're just considering something as simple as quadratics, for example, then we can very easily see that quadratics are either going to be purely concave up or purely concave down. However, we could be dealing with situations like cubics or quartics, where we're going to have regions which have a different concavity. So, for example, if I give you this cubic here, then we can see that if I just draw this dotted line, everything in this blue box here looks like it is concave down, whereas everything in this green box here looks like it is concave up. This can get even more complicated. We could consider a quartic graph that goes something like this, in which case, if I just draw some dotted lines here, in this region here and in this region here, we can see that we've got a concave up shape, whereas in this middle region, we can see that we've got a concave down shape. And as we progress through the rest of this chapter, we're going to notice that the concavity of different graphs can tell us a lot about the behavior of the graph, especially then when we link it to real-world applications. But more on that a bit later. Now, very similar to when we were talking about the first derivative in terms of increasing functions, decreasing functions, and stationary points, we've got to consider three different situations for the second derivative and how they tell us different things about graphs. So, here's a little bit of a summary. If the second derivative, so f double dash of x, is greater than 0, then we get a concave up shape. So in other words, it's going to have this kind of curvature here. If f double dash of x is less than 0, then we're going to have a concave down shape. So we're going to have something like this. Now these two here make a pretty easy amount of sense in that if we've got a positive answer for the second derivative, then we're going to be going up. And if we've got a negative answer for the second derivative, then we're going to be going down. So it's a fairly easy one to remember in that case, much like how the increasing and decreasing rules for the first derivative are pretty easy to remember as well. The interesting case that we're now going to be looking at, though, is what happens when f double dash of x is equal to 0. When we have the second derivative equal to 0, we have what is called a point of inflection, or an inflection point. The really important thing to understand about inflection points is that you've got two different types, and they both look very, very different, and they both can represent very, very different things. So the first one that we're going to look at is something called a non-stationary inflection. Now, non-stationary inflections are things that you probably would have seen quite a bit of already, especially when dealing with cubic and quartic functions. So if I just draw up a very rough cubic function, where you've got your maximum here, you've got your minimum here, then the point of inflection would occur somewhere about here, and this is called a non-stationary inflection. Now, here's a really important thing. When we're talking about the non-stationary inflection, if I just draw a dotted line up and down, in this particular case here, on the left-hand side, we've got a concave down shape. On the right-hand side, we've got a concave up shape. So essentially, non-stationary inflections, or just inflection points in general for that matter, are the points which separate when the graph is concave up and when it's concave down. At the point of inflection, it's neither. It's that midway point between the two of them. Now, the reason why we call this a non-stationary inflection is because it's not a stationary point. Because remember, stationary points are when the derivative is equal to 0. In other words, the gradient would be 0 and the tangent would be flat. But in this case, if we drew a tangent here, we get a non-zero gradient for that tangent. So it's a fairly straightforward name in that regard, in that it's pretty descriptive, non-stationary, meaning that it's not going to be a stationary point, but it is an inflection point. So I'm just going to write this here. This non-stationary inflection will occur when f double dash of x is equal to 0, but when f dash of x is not equal to 0, because it means that it is not a stationary point. The second type that we're going to have a look at, as you might imagine, is a stationary inflection. Stationary inflections are things that you've probably seen quite a bit of at this point. We in fact actually had a look at a few examples of this in the previous chapter, but that is where you could either have a curve that looks like this or a curve that looks like that. The stationary inflection occurs when the graph is flat. Now, very similar to before, if I draw a dotted line where these inflections are, we can see that on both sides the concavity is different. So with this first one here, on the left-hand side, it is concave down. On the right, it is concave up. With the second one, on the left, it is concave up. And on this side here, it is concave down. So again, the key application of inflection points on graphs is where we separate the concavity region. So in other words, when we go from concave up to concave down, or when we go from concave down to concave up. Now, in the stationary inflection case, once again, the inflections will always occur when f double dash of x is equal to 0. But now, in these cases, because they are stationary points, then the first derivative must also be equal to 0. So the reason why this is important is because sometimes in questions, especially in your test and exam, you will be asked to identify what type of inflection point it is. And in this case, it's fairly easy. You just need to also test out to see what the first derivative is at that particular point. If both the first and the second derivative are equal to 0, then you've got a stationary inflection. If only the second derivative is equal to 0, then you have a non-stationary inflection. But once again, the naming system is pretty straightforward in this case, so hopefully there won't be too much confusion there. What we can do now is quickly link what these inflection points mean to the actual context of different problems that you could be looking at. So let's consider a little bit of context. Let's first of all start with the stationary inflection. So that's ones that you've got like this and ones like that. Ultimately, non-stationary inflections don't tell you too much about the graph other than what we already know about stationary points, in that at stationary points, the graph is neither rising nor falling, so it's got that stationary aspect, and that at this particular case, the tangent to the graph is going to be horizontal. So you haven't really got much there that we didn't already know. However, when we are talking about non-stationary inflections, so ones where it looks like this is where something new comes out of it. So the key context of non-stationary inflections. And I'm actually going to draw out two different examples here just so we can kind of see what's going on. The inflection point will be about here. Is that at the inflection point, this is where the graph is going to be its most steep, whether it be a positive steepness or a negative steepness. But in either case, this is where the gradient is going to be its most steep, or in other words, when the gradient is either going to be its most positive or its most negative. So let me just write this out here. For non-stationary inflections, the inflection point has the steepest tangent. Both positive and negative considerations. So what that means for us is that this is when the graph is changing, whether it be increasing or decreasing, at its most rapid rate. So this is realistically the big practical application of inflection points. It tells us when the tangent is going to be its steepest, whether in the positive direction or the negative direction. But what this means in a more practical sense is it tells us when a particular quantity is changing at its fastest rate. Now, the reason why this could be quite important, let's give a good example of a medical thing. Let's say you inject a drug into a particular person. The effectiveness of that drug follows a cubic graph, for example. Then you will ultimately want to know when the effectiveness of that drug is changing, whether it be increasing or decreasing at its fastest rate. Another example could be a runner. If you had a graph that tells us how far a person is running over a certain period of time, then the inflection point would ultimately tell us when the person is running at their fastest pace, or just moving at their fastest pace. We're actually going to be having a look at a few good examples of this in both the kinematics section and the rates of change section, so I'm going to highly suggest that you watch those videos for some good examples there. However, coming back to this, again, I can't stress this enough. Whilst stationary points have their key application of being a maximum or a minimum value, the inflection points tell us when the graph is changing at their fastest rate. But again, this is only for non-stationary inflections. Stationary inflections don't really tell us too much that we don't already know. Now, just on a quick side note as well, second derivatives also have a very, very good application for something that we talked about in the previous chapter when we're trying to identify whether a stationary point is a maximum or a minimum or a stationary inflection. So let's have a good look at this. So we identified before that when the second derivative is a positive number, so it's greater than 0, then we get a concave up shape. On the flip side, when it's negative, so when f double dash of x is less than 0, then we get a concave down shape. Now, the really interesting thing about both of these is that in this first case, when f double dash of x is greater than 0, we can see that this particular curvature here only allows us to have a stationary point, which is a local minimum. Conversely, when you have the other side, so when f double dash of x is negative, so we have a concave down shape, this particular curvature only allows us to have a local maximum. So what this means is that if we are trying to identify what type of stationary point that we have, and if you didn't want to use a sign diagram for whatever reason, which is absolutely fine, then you can use what's called the second derivative test to find out whether it's a local minimum, a local maximum, or a stationary inflection. So in other words, if f double dash of x is greater than 0, and you know that you've got a stationary point, then this means that you're going to have a local minimum. Whereas if f double dash of x is less than 0, and again, you've got the first derivative equal to 0, so you know that you've got a stationary point, then this means that you've got a local maximum. And then, summarizing something that we already said before, if you've got the second derivative equal to 0 and the first derivative equal to 0, then this means that you've got a stationary inflection. Now, the reason why I bring this up is because this can be a very efficient and useful technique in replacement of sign diagrams to identify the nature of different types of stationary points. However, only use this if you're comfortable using the second derivative at this point. And on top of that, I would always suggest just going for the option which seems quickest and most comfortable for you. If you prefer to use sign diagrams, that's fine. If you want to use the second derivative test, that's absolutely fine as well. What I would actually like to quickly do is re-go over one of the examples that we did in the previous chapter to very clearly identify the nature of the stationary points, but in this case using the second derivative test. So this was the third example in the last theory video, where we had the graph y equals negative a half x power 4 plus 4x squared minus 8. So coming off of what we did last time, we found that the first derivative was negative 2x cubed plus 8x. So then the second derivative would be negative 6x squared plus 8. Now, we want to find out where the stationary points are, so we're going to set y dash equal to 0. Doing so, we get negative 2x cubed plus 8x is equal to 0. And then using our calculator, we get the answers of negative 2, 0, and positive 2. So we know that our stationary points are here, but now we want to try and find out if they're local maximum, local minimum, or stationary inflections. So we're now going to substitute these values into our second derivative and see whether we get positive or negative answers. So with the first one, at x equals minus 2, the second derivative will be negative 6 lots of negative 2 squared plus 8, which is equal to negative 16, which is a negative answer. Then at x is equal to 0, y double dash is negative 6 lots of 0 squared plus 8, which is equal to 8, which is a positive answer. And then finally, at x is equal to positive 2, then y double dash is negative 6 lots of 2 squared plus 8, which is negative 16, which is less than 0. So if we come back to the rules that we said before, if the second derivative is positive, it's a local minimum. If the second derivative is negative, it's a local maximum. And then finally, if the second derivative is equal to 0, then we have a stationary inflection. At x equals negative 2 and positive 2, the answers are negative. So these two here, we have local maximum. Whereas at this middle point, when x is equal to 0, the second derivative is positive. So this means that we're going to have a minimum. And what we can see is that this actually matches up with the answers that we had before. But the really good thing is here is that we didn't even have to use the sign diagrams or substituting in different values to find out where the regions of increasing and decreasing are. So like I said, use this method if it feels more convenient and more comfortable to you. In some situations, I probably would suggest using this one over sign diagrams. Conversely, there's going to be some situations where finding the first derivative and leaving it there is going to then be easier than finding the second derivative. Examples of that I can think of right now are stuff like the radical functions, which can be quite hard to find the second derivative for, and also reciprocal functions. Choice is completely up to you. You just do what's best for you. However, when I go through more and more examples of finding the nature of stationary points, I will be using a mixture of both of these rules here. So it's completely your choice as to which one you'd prefer to follow. Now, let's go through what types of questions you could be asked in this particular section here. Because very similar to last time, I've always found it very useful to be a bit more prepared for what types of questions you could be asked, just so then you understand what could be expected of you in terms of the actual maths. The first type of question you could be asked, and arguably the most simple, is to find the points of inflection. So in order to find out where the points of inflection are, the first thing you're going to do is to find the second derivative f double dash of x. Then you're going to set f double dash of x equal to 0, because we know that inflection points occur when the second derivative is equal to 0. And then you're going to solve for x. And then, if needed, and only if needed, you'll find the y coordinates. So that one there has a very, very similar approach to when you were just being asked to find out where the stationary points are. However, in this case, the only distinct difference is that you have to find the second derivative instead of just the first derivative. The second type of question then is to find regions where the graph is concave up and concave down. So in this case here, Similar to before, first thing you're going to do is find the second derivative f double dash of x. Then you're going to set f double dash of x equal to 0. And then you're going to solve for x. What this here does is those first three steps there solve for where the points of inflection are, because then what you can do is to create a sign diagram for the second derivative. And very similar then to how you would construct your sign diagrams for the first derivative, is you then need to put on where the points of inflection are using vertical dashes, and then in each region you need to test an x value with the second derivative. If that x value is positive, then you put a plus in that region. If it's negative, you put a minus in that region. And then we use those regions to identify the concavity of the graph in those different regions there. So then the last step is to write the intervals of concavity using interval notation. Similar to the last chapter as well, it's always best to write your answer to this kind of question in a sentence format. So in other words, the graph is concave up for x blah 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 blah, and it is concave down for x blah 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 blah, given the different regions. And then the third type of question that you're going to get is to find and identify the nature of the points of inflection. In these cases here, again, same first few steps. So you're going to find f double dash of x. You're going to set the second derivative equal to 0. You're then going to solve for x, because that will then tell us where the points of inflection are. And then you need to do the first derivative test. So you're going to substitute in solutions into the first derivative, f dash of x. If the answer is 0, then you've got a stationary inflection. If the answer is not equal to 0, then you've got a non-stationary inflection. So once again, you'll notice a very key distinct difference here between when you're trying to identify what types of stationary points you have and what types of inflection points you have. When you were trying to identify types of stationary points, you would either have to use the sign diagram for that, or you could use the second derivative test. However, when you're talking about identifying different types of inflection points, it can either be a stationary inflection or a non-stationary inflection. And the only way that you can find that is to substitute in the x values of the inflection point back into the first derivative and see if it's 0 or not, and then go from there. Now, from this, there generally is a big overarching question when it comes to these types of questions in tests and exams, and that is to then use all of this information, usually combined with stationary points and increasing and decreasing regions, to then graph out a relatively complex function. So for example, you could be given a cubic, a quartic, could be even a quadratic if they're feeling a bit nicer about it, but then you need to use all of your knowledge about where the stationary points are, where the points of inflection are, where the graph is concave up, where it's concave down, where it's increasing and decreasing, and so on, in order to somewhat accurately draw out the graph of different types of functions. Now, we will be looking at an example or two of this in the corresponding application video to this theory video, so I'm definitely going to suggest you have a look at them, because they can be relatively challenging questions, and in tests and exams, they're usually worth quite a few marks, so it's very important that you do everything right. Alrighty, now that we've covered all that, there is one last section of this chapter that I need to go through. And the reason why I've kind of separated this out from the rest of the chapter is because the ideas behind this last section here is a little bit different, and the types of questions that you're going to get on this generally a little bit harder as well. So I wanted to dedicate a bit more separate time to this little section here. Now, what this section here essentially asks us to do is we generally start with a graph of a function. We are then asked to use that graph to then draw the derivative function graph and then the second derivative graph as well. Conversely, you could start with the first or second derivative graph and then ask to go backwards to graph out the original function. Now, the really important thing about these types of questions is that generally speaking, they will always give you the important x coordinates, but they will never give you y coordinates because their main focus of these questions is to make sure that you understand how to transfer knowledge from one graph to either its derivative or backwards from the derivative to the original function. So, types of questions here could be using the graph y equals f of x, draw y equals f dash of x and or f double dash of x, or conversely, using the graph of y equals f dash of x or f double dash of x, draw the graph of y equals f of x. So there's two different ways these types of questions could go. However, the approach for them are borderline the exact same. The best way that we can have a look at doing questions like this is with a nice table of transformations between the original functions, its derivative, and its second derivative. So let's have a look at doing something like this. So let's list out all the important features for the normal graph f of x here. Then we could have the first derivative graph f dash of x, and then the second derivative graph f double dash of x. So, if the original graph has an x-intercept, then this tells us nothing about the derivative, and it tells us nothing about the second derivative. So that one there is pretty much meaningless. If we have a stationary point, then the way that this transforms into the first derivative graph is this is now going to be an x-intercept, and then to the second derivative, that tells us absolutely nothing. If we have a non-stationary inflection, then to the first derivative, this is a stationary point, and it cuts the x-axis. For the second derivative, this just transforms into a simple x-intercept. And then the last one, for a stationary inflection, for the first derivative, this once again is a stationary point, but this time it is just going to touch the x-axis. And we'll get into the key difference between this and cutting a bit later on. And then once again for the second derivative, this just turns into an x-intercept. This table here is going to be very, very, very helpful for when you are doing these types of questions, because if you can identify where the key features are on any of these graphs, then you can very easily go forward or backwards towards what those key features are going to look like for the other types of graphs that you could be working with. Now this here is the key table I wanted to bring up. However, the other one which could be very, very beneficial will be this one here. So once again, we're going to lay it out as f of x, f dash of x, and f double dash of x. So if f of x is increasing, then this means that f dash of x is above the x-axis. For the second derivative, this is meaningless. If f of x is decreasing, then it means that f dash of x is below the x-axis. And once again, for the second derivative, this is meaningless. If f of x is concave up, then for f dash of x, this means that it is increasing, or in other words, it's got a positive slope. For f double dash of x, this means that it is above the x-axis. And then conversely, if f of x is concave down, then f dash of x is decreasing, which means that f double dash of x is below the x-axis. So once again, this table here could be very, very beneficial for when you're doing questions like this. Understanding where the graph is going to be concave up, concave down, increasing, decreasing, or above or below the x-axis are all very, very important features and things that they're going to be mostly looking for when you are doing these types of questions. The other thing which I can highly recommend that you do with questions like this is to use sign diagrams. They're going to be very, very beneficial in transforming one graph into another, and I'll show you how you can use sign diagrams when we go for an example of this in just a few moments. Cool. Now that we've gone through all of that stuff there, let's actually go through a few examples of inflection points, identification, and also how to transform one graph into another. The first example that we're going to go through is the following. So we're going to have the graph y equals 3x to the power of 4 take 16x cubed plus 24x squared take 10x plus 1. And we want to find intervals where the graph is concave up and down. Okay, so in order to approach this kind of question here, first thing we need to do is find the second derivative. So before we do that, the first derivative, y dash, will be found using just the basic rules of differentiation. So that will be 12x cubed take 48x squared plus 48x take 10. So then y double dash will be equal to 36x squared take 96x plus 48. Now we know that the inflection points occur when the second derivative, y double dash, is equal to 0. So therefore 36x squared take 96x plus 48 is equal to 0. And then using your calculator to perform this calculation, we get answers of x is equal to 2/3 and positive 2. So these are where our points of inflection are. So in order to find out where the graph is concave up and concave down, we're going to need to construct a sign diagram. So I'm going to just draw this one over here. We've got x and y double dash labeled. We're going to have 2/3 here and we're going to have 2 here. We now need to test out values for x in the second derivative in each of these different intervals here. And that will allow us to figure out where the graph is concave up and concave down. So first things first, let's do this leftmost interval here. A point that fits in there is x equals 0. So at x equals 0, y double dash, so that's going to be substituting into this function up here, will be 36 multiplied by 0 squared, take 96 slots of 0 plus 48. That will give us an answer of 48, which is positive, so we can put a positive there. So then in this second interval here, a point that fits in there is x equal to 1. So at x equals 1, y double dash is 36 multiplied by 1 squared, take 96 lots of 1 plus 48, which gets us an answer of negative 12, which is negative. So we're going to put a minus there. And then finally, in this rightmost region here, a point that fits in there is x equal to 3. So we'll put at x equals 3. Y double dash is 36, lots of 3 squared, take 96 lots of 3 plus 48, which is equal to 84, which is a positive answer, so we'll put a positive there. So now by reading off of this sign diagram, we can tell that in this region here and in this region here, the second derivative is positive, so it means that we're going to have a concave up shape for both of these regions here, and this middle region here has a negative double derivative, which means that in that region there, the graph is going to be concave down. So now by writing this information as a final sentence, we can say the graph is concave down for 2/3 less than x less than 2, and the graph is concave up for x less than 2/3 and x greater than 2. The reason again why we have to write this one in separate notation is because these two intervals here are completely disjointed, so you have to make sure you do it in two separate interval notations. The second example we're going to look at is to find and classify all inflection points for the graph y equals 2x cubed plus 12x squared plus 24x take 7. So in order to find out where the points of inflection are, we need to find the second derivative. But the first thing that we're going to do is find the first derivative from this function. Using the basic rules of differentiation, this is going to be 6x squared plus 24x plus 24. And then the second derivative, y double dash, will be equal to 12x plus 24. So now we know about inflection points occur when the second derivative, y double dash, is equal to 0. So setting the second derivative equal to 0, so that's 12x plus 24 is equal to 0. Rearranging this to get x by itself, we get x is equal to minus 2. So we have a single point of inflection at minus 2, but now we want to also identify what kind of inflection point this is. A reminder that when we're talking about inflection points, we can either have a stationary inflection or a non-stationary inflection. And the way that we test this is we find out whether it is also a stationary point. So what we're going to do here is we're going to do at x equals minus 2, we're going to substitute this into the first derivative function, which is this one up here. So that is 6 lots of negative 2 squared plus 24 lots of negative 2 plus 24, which is equal to 0. So therefore, since y double dash is equal to 0 and y dash is equal to 0 at x equals negative 2, then there is a stationary inflection at x equals negative 2. And then the third and final example we're going to look at here is we're going to start with this graph here. We've got this local maximum here at negative 5. We've got a local minimum here at 3. And we're going to say that the point of inflection is at negative 1. And this here is the graph of y equals f of x. And the question is now graph y equals f dash of x. So when you're doing a question like this, as I mentioned before, the best thing that you can do is to label out and identify all the key important features of the graph that you are given. Once we have all those important features, we can then transform them into the graph that we need. So if we look at the information that we've got here, we've got stationary points at x equals minus 5, and at 3, we have a non-stationary inflection at x equals minus 1. What you could also do here if you really wanted to is you could then identify the regions where the graph is increasing or decreasing, and also concave up and concave down. However, just to save a bit of time, my suggestion here is going to go straight for a sign diagram for the first derivative. So we've got x, f dash of x. We know that we've got stationary points at negative 5 and 3. In the region before negative 5, so in other words, this little section here, we can see that the graph is moving upwards, so it's increasing. So then the first derivative must be positive. In the region between negative 5 and 3, the graph is going downwards, so the first derivative must be negative. And then in the region after 3, the graph is once again increasing, so the first derivative must be positive. So what this sign diagram here allows us to do is it allows us to understand when the graph of f dash of x is going to be above and below the x-axis, and then from these two here we can identify what kinds of points we're going to have. So we recall that stationary points at x equals minus 5 and 3. Well, what this here transforms into is that for f dash of x, we're going to have x-intercepts at x equals negative 5 and 3. And then the non-stationary inflection at x equals minus 1. Well, what that means for f dash of x is that we are going to have a stationary point at x equals minus 1. So what we can do now is we can use these two bits of information combined with the sign diagram to now graph out a somewhat approximate answer for the graph of y equals f dash of x. So the first thing I'm going to do here is quickly list out the important x points that we've got. So we've got negative 1, 3, and negative 5. We know that we're going to have a stationary point at x equals minus 1, but we also know that we're going to have x-intercepts at the minus 5, so we know that we're going to cut through here, and we're also going to cut through here. On top of that, Using the sign diagram, we know that everything in between -5 and 3 must be negative. In other words, it must be below the x-axis. Whereas to the left of -5 and to the right of +3, we know that it's positive, so it's going to be above the x-axis. So I'm sure you can kind of gather what kind of graph this is going to look like. We're going to have a turning point somewhere down here. And then this is going to continue upwards in this direction, and it's going to continue upwards in that direction there as well. And the only extra thing I would recommend doing in this case is just putting a nice dotted vertical line at the -1 to indicate that this local minimum is aligned with that -1 point there. Now, the really good thing about these types of questions is that if we come back to the original graph that we were given, you'll notice that we're never given any scaling on the y-axis. And what this essentially means for your answer is that you do not need to particularly worry about how high or how low any of your turning points or your points of inflection are. As I mentioned before, the key thing that they're looking for in these types of answers is making sure that you align up the x coordinates with the corresponding important point. So for example, are you putting the x-intercepts in the right place? Are you putting the stationary points in the right place? Do you have the right type of stationary point, and so on? So as long as you match up those x coordinates nicely, then you're absolutely fine. The y coordinates don't matter all too much. Alrighty, let's wrap up. So in this video, we delved into the concavity and shape of functions and how this links to the second derivative and inflection points. For a function f of x, inflection points occur when the second derivative f double dash of x is equal to 0. The function is concave up when f double dash of x is greater than 0, and concave down when f double dash of x is less than 0. We showed how the second derivative sign diagram can be useful in displaying the location of inflection points and regions where the function is concave up and concave down. There are two types of inflection points. Stationary inflection points occur when the first derivative is 0, and non-stationary inflection points occur when the first derivative is not 0. We showed how we can use the features of the graphs of f dash of x and f double dash of x to sketch the graph of f of x. We looked at how we can identify the nature of stationary points using the second derivative. Local maxima occur when f double dash of x is less than 0, and local minima occur when f double dash of x is greater than 0. Finally, we outlined useful strategies to locate and classify inflection points and regions of different concavity, and applied these strategies to some exam-style questions. And that's it for now. See you in the next video.